Hi, I'm Takahiro Sumi from Osaka University. I'm going to talk about a MOA-II free floating planet mass function. Okay, so as Przemek says, the gravitational microlensing is the only method to find the low mass free floating planet. And if the time scale of the microlensing event is the angular Einstein radius divided by the relative proper motion, and that is proportional to the square root of mass, and it's only 0.05 day for the Earth mass free floating planet. So if we can detect low mass free floating planets by finding the very short time scale microlensing. So indeed, we found several such short timescale events from the 2 years analysis of the MOA data sets, like this. This is the light curve from 2 years, and then this is the close-up. This timescale of this event is around 1 day. So we expect this is a Jupiter mass lensing object. However, we cannot definitely say this is a planetary mass because we cannot measure the mass directly. This mass degenerates with the distance and velocity in the time scale. So what we did is that we conducted statistical analysis by using the time scale distribution. Here is the time scale distribution from the 2 years of the MOA datasets of the about 500 events. For the longer timescale event, that can be explained by the existing population, like brown dwarf, main sequence, white dwarf, neutron star, and black hole. And we found some excess at the short timescale event. So we tried to explain these short events by introducing the new planetary mass population, like a free-floating planet or very wide orbit planets. Although this analysis have a very large uncertainty in the typical mass and abundance of the lensing object, this was the first attempt to find the free-floating planet by the gravitational microlensing. And then, as Przemek says, the OGO did a similar analysis with a higher quality dataset with larger number of the statistics. They found even shorter timescale events of like 0.2 days. So indicating the existence of the even smaller population like super Earth. So these two analyses make use of the time scale of the microlensing events. And more recently, Andy Go, he used the angular Einstein radius instead. So angular Einstein radius is a better indicator of the mass because the one of the degeneracy breaks. So he extracted 30 events with finite source effect in which they have a measurement of the theta E. So here is the cumulative distribution of the theta E. And he found there is the two distinct population, planetary mass object and the brown dwarf and main sequence star, and find the data they call the Einstein data. So indicating the distinct planetary mass population separated from the brown dwarfs. So the drawback of this analysis is that this event with finite source effect is rare. So the limited by the small number of the statistics. So it is better to use all information, including the time scale and also the Einstein angular Einstein radius. So in our analysis, we use both information of the time scale and also this theta E together. So not wasting any information on the mass of the lensing object. So the MOA collaboration is the collaboration between Japan, New Zealand, and the United States, observing at the Mount John Observatory in the South Island of the New Zealand. And we are using the 1.8 meter dedicated telescope. We have a very wide 2.2 square degree field of view. we are observing the tens of millions of stars towards the galactic bulge and reducing the difference imaging analysis to find any variable object. We are detecting all of the variable objects on the images which are not even visible on the reference images. And then we select only microlensing events. Particularly in this analysis, we focus on the single lens microlensing events. So there are many backgrounds. We removed all the variable stars, and also the other short time scale background is the short caustic crossing binary lens event. This is the only duration of the few hours during the years of the light curves. But you can see the clear caustic crossing signature like this. So we remove these binary events from our sample. Another background is this kind of flare stars, and also the fast-moving object, which creates this kind of short magnification in the light curve. And we carefully remove these backgrounds. Then after we analyzed the 9 years of the MOA dataset, we found the 6,000 microlensing events, but we only selected 3,500 high quality events by using the rather strict selection criteria. In this sample, we found 13 events with finite source effects, and the 2 of them have a very short time scale, less than 0.5 days. So this is a very likely free floating good candidate. Here is the one example, the light curve for the 9 years. Here is the peak. Here is the zoom up. And the time scale of this event is only the 0.07. So it's a very likely the Earth mass lens. But the apparent magnification is rather longer, about 3 hours. This is because of the finite source effect. So the finite source effect is very important, particularly for the detection efficiency changes because of this effect. And also we can extract the theta E, which have more information on the lens mass. So here the other events we found, So in this sample, we found 12 events with less than the TE is less than 1 day, and the 6 events are less than 0.5 days. So here's the other events with the time scale is less than 1 day. And the others. And this have a very clear finite source signal. And here is the 2 events, short events with finite source effect. The one theta E is only the 4 microarcsecond. From this theta E, we did a likelihood analysis and found this can be the super Earth or sub-Neptunes. And this theta E is only the 0.9 microarcsecond. So this is likely the Earth mass free floating planet candidate. Detail will be given by the Naoki's talk. So let's see the distribution of the angular Einstein radius theta E from our analysis. Here is the cumulative distribution of our 13 finite source effect events, and compared to the 30 events by the Gould et al. From the CAMT nets. You can see there is a similar gap around here, similar to the Gould et al., confirming that there is the Einstein desert in our sample as well, indicating there is a distinct planetary mass population separated from the brown dwarf like this. So the difference from the Gould et al. Distribution is their distribution is truncated at around here, the sub-Neptune or super Earth, but we found the one Earth mass free-floating planet here. So this is the second such Earth mass free-floating candidate after the Ogo 1928. So this is a confirmation of there is such population with such planet with the Earth mass object. not only the super Earth. So as I said, the finite source effect is very important. Not only for the detection efficiency, and also that we can use that information in our analysis. So we did image level simulation with finite source effect for the first time. So this is a very new feature of this analysis. Detail will be given by the Naoki's talk. So by using this 2D detection efficiency in the time scale and also the CDE, we conducted likelihood analysis to derive the mass function of the lens population by fitting to the time scale distribution. So the model event rates gamma is the function of the TE and the CDE by using the galactic model by the Koshimoto et al. And assume the mass function. Here we assume the power mass functions. Here is the salpeter-like mass function for the stellar object, and then power mass function for the brown dwarfs, and also the power mass function for the planetary mass object. Then we fix the power law for the stars, and then we fit for the power of the brown dwarf and the planetary mass object and the normalization. So here is the result of the likelihood analysis. We found the power of the planetary mass object is about 1. So here is our observed timescale distribution and also the best fit model. So as you can see, the time scale longer than 1 day can be explained by the brown dwarf, main sequence, white dwarf, neutron star, and the black hole very well. And there is the significant excess at the short time scale. That is confirmed the results from the oval. And the best fit model can explain this excess like this pretty well. And the best fit power for the planetary mass object is about 1. So from this model, we estimated the number of the free floating planets is about 20 per star, even with large uncertainty. And also this number depending on what range of the mass we integrate. So here is the mass function, best fit mass functions. Here is the mass function around the stars, brown dwarfs, and the planetary mass object. Shaded region indicating the uncertainty, and this orange indicating for the case of the broken power law rather than the single power law for the planetary mass object. So it's largely conservative uncertainty. So this gray indicating the mass function found by the microlensing, so the called bound planets. So this indicating there are more low mass FFP than the heavier one. And the power is steeper than that for the bound planets. If it about 0.6, if we assume the single power law for the bound planets. So this can be explained by the scenario. The planets may be formed around the stars, and then less massive star, the more frequently ejected to be the FFP. And then the FFP is about 20 times more abundant compared to the bound planets found by the microlensing outside of the snow line. So even though these are not free floating, they are still important to the bound planet, outer bound planet is more significant. So the Roman will detect low mass FFP by using our new mass function. Roman will detect around 1,000 FFP, and 600 of them are less than the 1 Earth mass, and we can get more accurate mass function by the Roman. And also, we constructed new 1.8-meter telescope prime at South Africa. This will be the first dedicated near-infrared microlensing survey. Will detect more bound planets and also the FFP. And we will conduct support observation to the Roman. If we did observe the same event from the Roman and the prime, we can measure the slightly different light curves, so-called space-based microlensing parallax. From this, we can measure the mass of the lens system. And particularly, this is the only way to measure the mass of the free-floating planets. And the formation scenario, I don't want to say detail because I'd like to hear more about this formation scenario from you guys during this conference. So here's the summary. We presented the first measurement of the mass function of the FFP. The power index indicating many Earth mass FFP. And they have formed around the star and probably scattered later. About 20 FFP per star. And this many information of the FFP is very important for the formation scenario because we need to know that not only the planet in orbit, but also the number of the planets scattered afterwards. Thank you.
Questions? I have a question. You said you fit for the timescale distribution. Do you? Why don't you fit for the Einstein ring distribution? Well, or did you?
Oh, we did actually. Yeah. So the detail will be given by Naoki. Yeah. Okay. But in the likelihood analysis, we have information on the theta E as well.
So really exciting the climate is going to be turning on soon. The thing that I was wondering, really exciting that the climate is going to be turning on soon. One thing I was wondering is what fraction of Roman FFP events do you expect to also pick up with prime?
We haven't actually calculated the detailed numbers, but we are detecting the events down to the 18th magnitude in the H band. So I don't know, some probably some 10% of something like that.
I have a question over here.
Oh, sorry.
Just out of the room. Great talk. That's really cool stuff. I had a question. So it seems like from your sample, a decent amount of the results come from the very shortest microlensing event you found. So what if just by chance the survey happened again, and because of some coin toss, you didn't have the shortest microlensing event? How would that affect the interpretation that you present?
So you mean the adding more data?
Yeah, no, so imagine so from this, the same MOA survey that you did, but just because of some coincidence in the sky, the shortest duration event did not happen. So how would that affect your conclusions?
So if we still have more data to analyze, and also the overall and the KMT is coming. So if there is such a the population, that we can confirm by the other data sets. And of course, the Roman will confirm the results.
But in principle, your statistics should account for the Poisson probability.
Right.
So it should be in the early post. Yeah.
So that's why we have a still larger statistical error.
Yeah, so to clarify, if you delete the lowest mass data point that you have, or the lowest data E, the resulting power law is still within the error bar.
Yes, we tested. Yeah, we tested removing the Earth mass planet, but still we have almost same power.
Okay.
So it's consistent with the higher, the heavier mass objects.
Okay.
Okay. Thank you.